Hello everyone. In this video we will talk about Taylor's theorem, which is a result on the error bound if we cut off our Taylor series and look at a Taylor polynomial to approximate our function. Alright, so first I want you to recall exactly what a Taylor series is. So the Taylor series for a function f of x centered at x naught here looks like the sum of an times x minus x naught to the n, where our an is exactly the nth derivative at your base point over the corresponding factorial, n factorial. And so I just want to be clear here, right? This only works if the nth derivative exists, right? For all n at your base point. So essentially this limits us a little bit in terms of what functions have a Taylor series centered at a specific point. But for a lot of the ones we care about, like e to the x, sine x, and cosine x, those work everywhere and in fact even converge everywhere. Now a lot of the times in practice this isn't too practical, right, to compute infinitely many terms. So a lot of the times it's good enough for us to get an approximation by cutting off our series at some point, say n, and then we get the nth degree Taylor polynomial or nth order Taylor polynomial, which stops at, well, it's nth degree, so it stops at the nth power here. Okay, so basically we just cut it off, and a lot of the times this is good enough, and that's basically what we're going to investigate in this video. So what does the error look like when we cut off at a certain point? Okay, so this is actually the statement of Taylor's theorem. So this is about the error. So if f is infinitely differentiable for all x in some interval I containing the base point, right? So we just pick any interval, and basically so long as all the derivatives exist in there, then we can get some upper bound on our error. And so the other thing that we require, this is going to look a lot like our error bounds for Riemann sums, right? Something like this. We're bounding the n plus first derivative here. And in this case, right, this k n plus 1 would be a constant. And so that's going to be your upper bound. So if we have this upper bound on the derivative for all the points in our interval, then our error term, right, so f of x is your actual value of your function, Pn of x is your approximation, and so this is exactly the error, is bounded above by this formula. Okay, so let's take a minute to figure this out. So the kn plus 1 is coming from our upper bound on the derivatives, and then the n plus 1 factorial kind of makes sense coming from our an term. And what this is doing here is saying basically the farther you are away from your base point, the more error you're going to have, right? Because if you're like 20 away from your base point, then this is 20 to the n plus 1th power. If you're only like 2 away, it's 2 to the n plus 1th power. And so the farther away, the less accurate you're going to be. And so the more terms you're going to need from your polynomial to be accurate. So let's go ahead and look at an example. All right, so let's look at sine of x. So, we'll just put up the Taylor series there, right? And this has the base point 0. It's centered at 0. And so my question here is if we go 1 down the line, right? Sine of 1, that's not on our unit circle, so we would need like a calculator to figure that out. How many terms of this Taylor series, like basically where do we need to cut off to ensure that we are within 1,000th of the actual value of sine of 1? So here we can use Taylor's theorem. So first of all, our interval that makes sense here, right? We have to include the base point, so we've got to include 0, and then we want to go to 1. And basically you want your interval to be as small as possible, because otherwise the bigger it is, the more terms you have to consider, and so that upper bound might be bigger for the n plus 1th derivative. So let's just go from the base point, include nothing to the left, and go to 1 and include nothing to the right. This is kind of the smallest interval we could use. Okay, so then we get our k n plus 1 by bounding the n plus 1th derivative, right? So yeah, call this f of x up here. So the n plus 1th derivative of x on this interval. And in general, right, what do these derivatives look like? Well, it's always either we go sine to cosine to negative sine to negative cosine and then back around, right? And then we just loop it. And so all of these, if we're on the interval from 0 to 1, well, at 0, we do get up to 1, but of course we never get bigger than that in absolute value, right? So we can say it's less than or equal to 1, and that will be our k in plus 1, right? So this is the upper bound we can use. And so with our formula, right, we just plug things in. Our f of x, or f of 1 is sine of 1 minus whatever our nth degree polynomial is. We need to figure out n of 1. This error is less than or equal to kn plus 1, which is 1, over n plus 1 factorial times the absolute value of x minus x naught to the n plus 1. Here, maybe I'll go ahead and just do this in 2 steps. And so what is this? This is, right, this was 1, and then x is 1 here, and x naught is 0, so this just disappears, right? So basically, our error is 1 over n plus 1 factorial. So then our question becomes, when is 1 over n plus 1 factorial less than 1 over 1,000? Well, that happens when n plus 1 factorial is greater than 1,000. And then you just kind of do it out, right? So I'll eliminate the first few, right? N equals 5, we get 6 factorial, which is 720. And then n equals 6, we get 7 factorial, which is 5040. And so basically, this is our answer. Once we get to the 6th degree polynomial, which is x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, and then, right, you have like 0 x to the 6th. This guy would be enough, and so really what we're saying, right, is p6 of 1, which is 1 minus 1/6 plus 1 1/20th, is within 1 1,000th, 1 1,000th of sine of 1. And so for your exercise, I want you to find the n necessary to estimate sine of 2 within just 1 100th, right? So we're a little bit farther away from the center here, and so you might expect there to be more error, so you probably are going to need more terms than you did to get it within 1,000th. So I'm just having you do it within 100th, see what happens there. All right, thanks for watching.